All right, so the last thing that we're going to talk about in this section, 14.5, is actually a return to something you talk about all the way back in Calculus 1. It's implicit differentiation. Remember, the way that we think of implicit differentiation, say you have a function y, y as it's a function of x, but it's not written in a form where y is isolated. You know, y equals some function of x. You might have an equation where x and y are appearing on one side of the equation, and we just think of y implicitly as a function of x when we do the differentiation. So a way of writing that in the form of a two-variable function, we can write f of xy equals 0. You can imagine moving everything from the equation over to the left-hand side. You have a function of x and y and a 0 on the right. And we think implicitly of y as a function of x, even though it's showing up here. X is also a function of x, it's itself, right? So both of these variables can be thought of as a function of a single variable, x. That means that we can apply the first case of the chain rule to these because both of these are functions of the same variable. So if I differentiate both sides of this equation with respect to x and use the chain rule on the left-hand side, this is what that would look like. It's the partial of f with respect to x times dx dx, plus the partial of f with respect to y times dy dx equals 0, because the derivative of 0 is still 0. Now dx dx is just 1, exactly like you would think it would be. So this reduces down to partial of f with respect to x plus this other stuff equals 0. You can solve this for dy dx and get the following. This is one version of what we call the implicit function theorem. We'll give the other version in a minute after we do an example. And I just want to show you what we would do with this. So first of all, this is saying that dy dx is equal to negative partial of f with respect to x over the partial of f with respect to y. This notation is just a little bit more convenient, the subscript notation. Let's see if we can do an example where we need this. We have this equation here. It's an equation, and y is understood implicitly to be a function of x. Cosine of xy equals 1 plus sine of y. Our goal is to find dy dx. Now you can try and do this using the Calculus 1 technique where you differentiate both sides with respect to x, and it's doable, but we want to try using this thing called the implicit function theorem. So first of all, this capital F here in the implicit function theorem is f of xy. It's what I get if I move everything over and get a 0 on the right-hand side. So I need to start by writing cosine of xy minus sine of y minus 1 equals 0. And this is the thing that I'm going to call f of xy, just the stuff on the left-hand side. So if that's f of xy, then what is fx? Because you notice in the implicit function theorem we need that. Fx is the derivative of this with respect to x. So that's going to look like negative y sine of xy. That's the derivative of this first term with respect to x. Notice that this sine of y and this 1 are both going to go to 0 because these would all be treated as constants. What is fy? Differentiating with respect to y, I'm going to get negative x sine of xy. I can differentiate this now because it's got a y in it, minus cosine of y, and that minus 1 still goes to 0. The implicit function theorem says that dy dx is equal to negative fx over xy, or negative so if I made a quotient out of these, everything has negatives in it already, you notice? So those would all cancel out, but then I'm supposed to make everything negative again. So let me just write it this way. I pull the negative out. Y sine of xy over x sine of xy plus cosine of y. Okay? Now the benefit of this theorem is if you try doing this using the Calculus 1 technique, you remember the differentiation part is really the easy part. It's just taking a derivative of this thing. But the difficulty is that you get a couple of dy dx's that pop out in that process, and you have to algebraically solve for dy dx. Depending on the example, that might take a little bit of work. Here, we didn't have to solve dy dx is isolated by default using this technique. And finding, really this just amounts to finding a couple of partial derivatives, which is usually not that difficult, and then sticking them into this formula. Okay, so that's pretty nice. Dy dx is given by this. Let's move up a variable though. Let's suppose that we have a function z equals f of xy. So z is a function of x and y. X and y are independent variables here. And let's suppose we have an equation that implicitly defines z as a function of x and y. It relates those things. So capital F, it's a different f than this one. Capital F of x, y, z is equal to 0. Because z is a function of x, y, we can write this way. Substitute for z, this f of x, y, and we see that this entire thing is a function of the two variables x, y, x and y. That means I can apply the second case of the chain rule to this thing if I want to find the partial derivative with respect to either x or with respect to y. So let's try that. If I tried the partial derivative of this thing with respect to x, I'd have to differentiate both sides with respect to x. The chain rule says I would get this expression right here. Partial of f with respect to x times the partial of x with respect to x, and blah, 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 all this stuff. Okay, that's just the chain rule. Now, a couple of these terms are worth noting. Partial of x with respect to x, that's equal to 1, in the same way that dx is equal to 1. Partial of y with respect to x is equal to 0. And the reason why that's the case is because we're assuming that x and y are independent variables. Y in this example is not a function of x. So you cannot have, well, let me back that up. You can have a partial derivative of y with respect to x, but you're thinking of it like the function's a constant. This just goes to 0. That makes this entire term disappear. So using those two facts, this simplifies down a lot. Partial of f with respect to x plus partial of f with respect to z times partial of z with respect to x equals 0. I can solve this for this guy, partial of z with respect to x, which we'll see what that looks like on the next page. But that's just for the partial of z with respect to x. I can also take the partial of z with respect to y and follow similar steps in order to do that. This is what gives me that more general version of this implicit function theorem that we've been talking about. So these are the two results that we would have gotten from following those steps in that previous little discussion. Partial of z with respect to x is equal to negative partial of f with respect to x, partial of f with respect to z, similar for partial of z with respect to y. This is, you can see the similarity between these results and what we got for our previous version of the implicit function theorem. So this will be our last example. Let's suppose that we have this equation, x squared minus y squared plus z squared equals minus 2z equals 4, and we also understand that z is implicitly a function of x and y. I want to find the partial of z with respect to x and the partial of z with respect to y using the implicit function theorem. So looking at what we need, we first need this capital F. What is capital F? Well, like before, that function capital F is what you get when you move everything over to the left and have a 0 on this side. So I'm going to have x squared minus y squared plus z squared minus 2z minus 4 equals 0. Okay? Now what I need is to think of this left-hand side as f of x, y, z. And I need to differentiate this thing with respect to all three variables, x, y, and then you see the z showing up in a couple of places. So what is the partial derivative of f with respect to x? That's pretty easy. X only shows up here. Everything else is going to look like a constant. That gives me 2x. What's my partial of f with respect to y? Again, y only shows up in one place. It's negative 2y. What's the partial of f with respect to z? Well, z shows up in a couple of places. It's equal to 2z minus 2. Okay. So, from the implicit function theorem, my partial of z with respect to x is going to equal negative partial of f with respect to x, that's 2x, over partial of f with respect to z, that's 2z minus 2. 2x over 2z minus 2. Simplify that by dividing the 2's out of there. That's going to give me x over z minus 1. Okay? X over z minus 1. One thing I'm forgetting, though. I forgot that I'm supposed to put a negative there. So let's go ahead and do that. Negative. Negative. Okay? If you want, sometimes people like to do this. You can bring the negative down into the denominator and call that x over 1 minus z. That's also fine to do. Let's do the same thing, but we want the partial of z with respect to y this time. That's equal to negative 2y over 2z minus 2. Again, using the implicit function theorem, this version of it. I'm going to use this negative to cancel that one, and then I'm also going to cancel all the 2's. Y over z minus 1. There's our answers. Okay, that's it for the chain rule.